three manifold. In a compact three manifold. Codimension 1. I am talking about codimension 1. Almost all the talk is referring to codimension 1 foliations. Almost everything. Almost. In the negative, we have this important paper for ATNGs. I will come back to this paper later, where he gives the first example of a manifold that cannot be realized as, or cannot be homeomorphic to a leaf of any codimension 1 foliation on a compact manifold. Probably the method of proof in this paper is the method of proof of every non-leaf in a codimension 1 foliation in the in the topological category, because there are a lot of deformations of this question. And in the same year, we have also this paper of this Japanese team of these guys that essentially gives new examples, but in the C2 category. Regularity matters in the questions of non-leaves, in the question of realization of manifolds as leaves of foliations. So the first historical results, both positive and negative, were addressed on codimension 1 foliations, being positive in the case of surfaces and appearing first examples in dimension 3 and bigger. So here are some a result about what we can expect about generic leaves. For generic leaves, we have some results about how must be the number of ends. This is an abstraction to some manifolds appears as generic leaves. So what we want to address with this remark is that probably if you want to realize a very complicated, topologically complicated manifold, you have to deal with the less accessible part of a foliation. It should appear in strange parts of the foliation. So the other flavor on the realization problems are the geometrical flavor, when a manifold is quasi-isometric to a leaf of a foliation. Here I remark this result of Sullivan in this paper of the 83, where he is able to give abstractions for some Riemannian metrics to be leaves of foliations depending on some invariants, topological invariants about the homology of the ambient manifold. These are asymptotic invariants, and these are also generalized in this other paper of also in 1983 of Tadeusz Jędrusiewicz. And here appears the same examples of Riemannian manifolds that not quasi-isometric to leaves in situ codimension 1 foliations, but they are homeomorphic to leaves. Okay, so it's something that has to the idea has to be perform perturbations in the metric in order to be sufficiently odd in order to not be realized as a leaf of a foliation. Codimension 1 and regularity. So regularity is something that is going to be important in the problem. We also make here another important result of Duminy that tells us how is the space of ends of a semi-proper leaf of an exceptional minimal set in a class 2 foliation of codimension 1. And there are a lot of papers of Cantwell and Conlon that are very important in all this theory of realization of manifolds in codimension 1. And if we are assuming some regularity, class 2 regularity, transversal regularity, we have these two papers that are separated by 20 years, but there are a lot of work in the middle. But I remark these two, Poincaré-Bendixson theory for leaves of codimension 1 in 81, and sets of exceptional leaves, where probably is the most general version of the Duminist theorem already published, as far as I know. Essentially, what is established in these papers are the theory of levels for C2 or class 2 codimension 1 foliations. What is the theory of levels? We can make stratifications in codimension 1 class 2 foliations. Being the first stratum, the minimal sets, formed by the minimal sets. And then what we have in class 2 foliations in compact manifolds is the existence of local minimal sets. So the second stratum should be the local minimal sets of the complement of the minimal sets, of the union of the minimal sets. And you can play this game so on, and you have some levels. Each stratum is a new level, where leaves in each level are accumulating to the next level. Yeah. C2 is important because for otherwise you have even not know if the existence of local minimal sets is not warranted. Okay. So one of the main corollaries of these results are that when you have periodic ends were defined by Hector in his talk, and it's important for this talk also, very important. If you have periodic ends for, you have isolated ends on proper leaves, whose limit set is formed just by proper leaves, then in class 2, this end should be periodic. Yeah, this is a consequence of, in fact, an isolated end cannot accumulate, cannot have in its limit set an exceptional minimal set, because by Duminist theorem, this should imply the existence of infinitely many ends accumulating from that, and this is impossible in an isolated end. So isolated ends of proper leaves should be periodic. This is also a consequence of Koppel's lemma that I am not going to address here, but this is an important fact that we have with regularity. And I have also to speak about some of the contributions of Paul here. He has shown examples of how to produce Riemannian metrics of bonded geometry that cannot be quasi-isometric to leaves of foliations, again, codimension 1. And he also oriented Fabio Sousa, that he were able to obtain examples of new examples of non-leaves of codimension 1 foliations, but in the same spirit as in the ETNG's paper that I talked before. And in fact, more or less at this time in 2013, I came to Rio and we began to try to understand another old problem in foliation theory, that is if exotic R4 can be realized as leaves or no. I will talk about this later. Well, this is more or less a picture of what a periodic end is. Observe that we have a periodic segment that is repeated again and again by a diffeomorphism or by a homeomorphism or by a quasi-isometry. This depends on in what category you are working. For instance, the counter example that you have in the paper of Januszkiewicz is topologically periodic, but is not isometrically geometrically periodic. No? And this is a constant in the theory of non-leaves. All the known examples have some kind of non-periodicity in its ends. So it's time to give some definition. What is a non-leaf? So it depends on in what category you are working on. So it's a topological, a smooth, generic non-leaf. Is a manifold that is not a homeomorphic, diffeomorphic, or quasi-isometric to any leaf of any and I add here codimension 1 foliation and compact manifold. I add codimension 1 because almost nothing is known for codimension 2. I will speak a little bit about this in a few moments. Even in codimension 1, there are few examples. It's not easy to produce examples. For instance, the example of Etienne, the first example given by Etienne, is a connected sum of lens spaces with increasingly greater fundamental group. There is a lot of technology to develop to reach the conclusion that it cannot be realized as a leaf of foliation. But all the known examples satisfies these two things in these two categories: topological and smooth. Geometric is a little bit, you have more technology to develop here, but here all the known examples satisfy that the ends are non-periodic, and there exists what we call a rigid block. A rigid block is just a compact set such that any copy of any homomorphic copy of the compact set inside the manifold must intersect the previous compact set. Yeah? Yeah. Sullivan. Yeah. Or what's it? Yeah. There's a difference. Yeah, the usual definition of quasi-isometry, I mean. I'm not sure if there are actual difference, but okay. No, Gromov. Then it's Gromov. Gromov. It's Gromov, yeah. Okay, so all the known examples satisfy these two kinds of things, and the question is if these two things are necessary or are able to give a criterion for non-leaves, a general criterion, not just examples. Criterion for a manifold to be a non-leaf in some of our categories. And of course, here began the questions: what about higher codimension non-leaves? If there exists something like that, if there exist manifolds which are leaves in codimension 2 but are non-leaves in codimension 1, this is trying to address the boundary of the problem between codimension 1 and codimension 2. And as far as I know, there are no examples in any of these directions. And now it's time to speak a little bit about higher codimension, codimension 2 and higher. And I want to address this paper of 1996 of here, there is another guy here, that's Oliver Atty and Steve Harder. But this is an important paper. There are new examples, again, of non-leaves in codimension 1 foliation, foliations, non-leaves that are homotopic to leaves. There are a lot of new things, but there is a new invariant for Riemannian manifolds that is called entropy of Riemannian manifolds, that essentially what is measuring this entropy of manifolds is how far the end set of a leaf of a manifold, of the manifold is from being a tiling, because a tiling is something that should be close to be a leaf. No? The leaf in a compact manifold should have a recurrence, and this kind of recurrence can be seen as a tiling in some sense. So one of the important things that finite entropy does not depend on quasi-isometric class of the metric, and so the entropy of leaves is upper bounded by the entropy of the foliations in the sense of Gis, Langevin, and Balzac. You are here, so as I said, there are a lot of works of you in this paper. So the corollary is that in Riemannian manifolds with infinite entropy cannot be quasi-isometric to leaves of class 1 codimension 1 foliation, because in class 1 you can obtain a finite bound for the entropy of the foliation. And it's relatively easy to obtain for any Riemannian manifold a Riemannian manifold of bounded geometry with infinite entropy. So any manifold, any open, of course, whenever I talk about manifolds, I am talking about non-compact manifolds. Any non-compact manifold admits such kind of metric. But I am interested in the converse. Before the question, I want to comment this result of Alvarez and Barral, where they in fact show that every Riemannian manifold is isometric to a leaf of a lamination on a compact space. So what this result gives us is that the question about realization is important for manifolds. In laminations, if you allow Baird spaces, you can realize everything. Yeah? Bounded geometry. Of course, every manifold with bounded geometry. This is a necessary condition to be a leaf in a compact space, of course. Okay, so let's summarize the questions. First of all, this is a question that is in some problem set, probably 2003 or 2012, I'm not sure. And it's can isolated ends of leaves of class 1 codimension 1 foliations added proper codimension 1 class 1 codimension 1 foliations be non-periodic? This was a question. I will try to address that that yes, it's possible to obtain non-periodic examples in class 1 codimension 1 foliations leaf. Is there a codimension 1 non-leaf that can be realized as leaves of codimension 2 foliation? The answer is I do not know, but in class 2 it's very easy, or is possible to obtain examples, and as far as I know, these are the first examples of this kind. Is there any class 2 codimension 1 non-leaf that can be realized as a leaf of some class 1 codimension 1 foliation? And again, the answer is yes. And more or less the same example works for the 3 questions. So we answer 3 questions with one example as a good example. And just to go to the work of Paul and me, is there any codimension 1 contractible non-leaf in class C1? Exotic R4s are the conjectural examples that should be. Paul and me show it that some of them are non-leaves in class 2. And what I am going to tell you is the idea that one of these guys should be, is a work in progress, should be a non-leaf in any regularity. Exotic R4s. And with health manifolds, if your construction is periodic, you can easily realize the Whitehead manifold in a generalized real component. Hector talked about this in his talk. But you can construct this kind of alternatives to the Whitehead manifold with non-periodic construction in the end. And almost nothing is known about if these non-periodic Whitehead manifolds can be realized or not in codimension 1 foliation. And this is a very interesting question. And the main point is that although the construction is non-periodic, it's very difficult to show that the manifold is indeed topologically non-periodic. Show that something is topologically non-periodic is very, very hard in general. Because you can have a wild homeomorphism to a periodic end. And it's very difficult to understand if this is impossible or not. And the answer and the question relative to entropy is if this is true that any smooth manifold admits a Riemannian metric of bounded geometry with finite entropy. I said that any manifold, non-compact manifold, admits a Riemannian metric of bounded geometry and infinite entropy, because you can perturb in a weird form your metric and obtain something that cannot be realized. But this is very difficult to show. Probably, I am almost sure that this should be true, that you can obtain this kind of metrics. But it's very hard to show. And I pose this as an open question. As far as I know, is open. But if it was false, I believe that is true. But if it were false, it would lead to unsmooth non-leaf in any codimension, because the result of harder and a t works in any codimension. So this question works to be studied in a deeper way. So in order to try to establish some kind of global criterion for non-leaves, I will define what is a rigid manifold. A rigid manifold is just a manifold such that any realization as a leaf, I should include here as a proper leaf, any realization as a proper leaf, dimension 1 oriented foliation admits a neighborhood which is foliated as a product foliation. Something that is rigid, and this is what motivates the definition. Non-leaves are rigid manifolds because they cannot be realized in any way. In any way. So, and there is a weaker notion of rigidity that is almost rigidity. If any realization as a leaf of a compact manifold is proper. Okay, this is something that is weaker than the previous definition. The rigidity in codimension 1 foliation comes to use the Dippolit's octopus decomposition in each side of a proper leaf. If your leaf has some good or bad behavior, topological behavior, you can show rigidity for some manifolds. For instance, the GIS manifold is rigid. Of course, it's a non-leaf, so it's rigid, but one of the steps of the proof is show that it's rigid. Yeah? Sorry. Any no, sorry, no, our manifold is by property that it does not accumulate to itself. It is not containing its proper in its limit. Okay. The limit set of the leaf does not contain the leaf. This is a almost rigidity is much more easy to obtain, because if you have a simply connected rigid block, you can use reverse stability. So this rigid block must be copied in a neighborhood of the manifold, and if the manifold recurs to itself, it has to meet this block infinitely many times, but the rigid block must meet itself. So this is impossible. So almost rigidity is something that is much more easier to achieve in any codimension. But rigidity is much more complicated. I don't know any criterion for rigidity in codimension 2, for instance. So it's simpler questions than the question of non-leaves. So probably if we want to understand the problem in codimension 2, we have to understand rigidity in codimension 2 foliations. Okay. And here a criterion for C2 non-leaves. If you have a manifold that is almost rigid with a non-periodic end, and it has finitely many ends, then by the theory of levels, Duminis theorem, Koppel lemma, etc., you cannot realize this guy in a C2 foliation, because the periodic ends, the isolated ends must be periodic with all these conditions. So find C2 non-leaves is not so difficult if we combine all the results of the 80s and 90s. Yeah. So okay, I want to talk about the answers for these 3 questions. because this should be interesting to the audience. The idea to motivate the example is to understand another paper of Etienne, an example of Etienne. So I have to introduce what I call GIS manifolds. So what is a GIS manifold? A GIS manifold is constructed by the addition of blocks in a sequence. So a GIS block is just a compact manifold of dimension greater than 4, such that the fundamental group is free abelian of rank greater than 2. And the boundary consists of two connected components, both homomorphic to the boundary of a solid torus. The meridian of one of these guys is homotopic to one generator of the fundamental group, and another one is homotopic to twice another generator. And more or less, this is a way to picture a GIS block. You will have, for instance, something with a abelian group at T3, and you remove tubular neighborhoods of representatives loops that represents generators, one and twice another. Given a sequence, you can glue these blocks following the sequence. The main result of Etienne, this is what we call a GIS manifold. It's a manifold that is obtaining union, making the boundary union of a GIS block with another one, gluing this part of the boundary with this one, okay? But it depends on the topology of the GIS block. No, it's not. It must have a abelian fundamental group. Yeah. This is T3, yes, of course. Without something removed, okay? But in dimension 4 and greater, this does not affect to the fundamental group, so it's a way to make a picture of what is going on. So the important result in the paper of Etienne is that two GIS manifolds are homomorphic if and only if they are related by the shift. So if the sequence is non-periodic, the manifold is non-periodic. So it's an example of a manifold which is non-periodic by the work of Etienne. My first idea is, it's possible to realize a GIS manifold in a codimension 1 foliation. It's possible. A non-periodic GIS manifold is possible to realize in a codimension 1 foliation, and the answer is that some of them, yes, is possible. Yeah. Well, GIS invented these manifolds to obtain a codimension 2 foliation with an exceptional minimal set, such that pairwise different leaves of the exceptional minimal set are not homomorphic. This was the interest of Etienne in this kind of manifolds. And in fact, there is a interesting question in the GIS paper that make this kind of example in codimension 1. Is possible, but it's much more difficult, because if you think in codimension 1 exceptional minimal sets, the semi-proper leaves have infinitely many ends if you want this regularity. So, and the GIS manifolds have 2 ends. So the example in codimension 1 is a little bit more trickier. So, but it's possible. I have the example, but it's not still written, but this is possible. Yeah. Well, he uses a horseshoe in a sphere. Inside the horseshoe, you have a exceptional minimal set, and are the sequences that you have there. So are not explicitly, but they exist. Okay. Okay. Well, this is a picture of a GIS manifold. So these are the blocks, but the blocks are coloring by topology, depending if the element of the sequence is 0 or it's 1. Okay, so the proposition is, the idea is, if I want to convert a GIS manifold in a non-leaf, I can glue a rigid block. Okay, we have no rigid blocks in a GIS manifold, but I can make a connected sum with a lens space, for instance. Something with finite fundamental group, cyclic, and the fundamental group of this guy is an amalgamated product of, well, there's the free product with the finite fundamental group of the rigid block, and you can show that this manifold is almost rigid. So it's a C2 non-leaf. Okay, so here we have a C2 non-leaf, very easy. So just glue a block here, and this is almost rigid, and so it cannot be homeomorphic to any leaf, any codimension 1 C2 foliation a compact manifold. So for free it's a C2 non-leaf, or almost for free. There is some work to make here. But for the specific case of T3 times S2 and T5, two GIS blocks in dimension 5, well, you have to remove here neighborhoods but of generators of the fundamental groups of these guys, but there are manifolds with dimension greater than 4 and abelian fundamental group. So here there exist sequences such that this manifold, non-periodic sequences such that this guy is homeomorphic to a leaf of codimension 1 C1 foliation on a compact manifold. And moreover, it's also homeomorphic to a leaf of a C infinito codimension 2 foliation. The second is essentially the same that the same ideas used by Etienne. So there is nothing new there. But in the first statement, it's much more complicated. I talking about this in Vienna in the summer, and it's a very complicated construction. But I'm not going to make the whole construction. I'm going to speak about how this foliation is constructed in general terms. But what is interesting here is that the ends of the foliations that I are able to construct, the sequences must be repetitive, are non-periodic but are repetitive. Any large sequence in the end repeats infinitely many times. So this addresses the question to repetitive ends. It's possible to obtain non-repetitive ends in isolated ends of proper leaves of codimension 1, class 1 foliations. So how the sample goes? Well, the main part is this. Let's construct a good foliation with a transverse boundary that has two boundary components. These two boundary components must be diffeomorphic, that are product foliation with S1. The other factor is the boundary of a solid torus. And in these circles, these transversals that we have to the boundary, transverse boundary of this manifold, we are in two intervals, I0 and I1, such the saturations of these intervals are product foliations with GIS blocks. How this is obtained is based in some old construction of Cantwell-Conlon. Originally, they used this construction to realize Markov pseudogroups in codimension 1 foliations, but this construction is very flexible to do a lot of things. And one of the things that you can do is this kind of foliation. So what is the idea now? Choose a Danjois map. So here comes the class 1 restriction, so that the exceptional minimal set of the Danjois map is contained in these intervals that we have here. So dynamically, we have this construction. This is the transverse circle of one of the boundaries. This is transverse circle of the other boundary. We have a Danjois diffeomorphism, that is what we use to glue the boundaries of the GIS of the leaves of the foliation. And the green points here is the Cantor set, the exceptional minimal set of the Danjois diffeomorphism. And what is going on is that the Danjois diffeomorphism always is gluing boundaries that belongs to these saturations of these intervals that are Gibbs blocks. So the leaves in the exceptional minimal set are Gibbs manifolds. And the fact that they're rational, the rotation number of the Danjou diffeomorphism is rational, implies that this sequence, the sequence associated to Gibbs manifolds, must be non-periodic. Okay? But I said that I have a C-infinity a realization a proper as a proper leaf, and these leaves here are not proper. But the leaves in the gaps, in this part of the gap, sufficiently close to the exceptional minimal set, still share the same combinatorics of what is going on in the exceptional minimal set. The difficult part of the foliation comes here in these two intervals. Here can happen wild things, but the gaps apply to each other gap only once. So if we are sufficiently close to the minimal set, when this gap goes to this other gap, still we are sufficiently close to the minimal set, and we never return to this gap. So we get proper leaves that are Gibbs manifolds. Now with a surgery procedure, you can place the rigid block in this manifold. And now about exotic R4s. I don't know how much time I have. I think that I have a little 10 minutes maybe, or
It's okay.
Okay, now it's about exotic R4s. This is another kind of stuff. This was mainly what I was working with Paul around these years in Rio. It was an old conjecture in foliation theory, and part of the initial question is still open. First of all, I want to address what are the kind of exotic R4s that we are going to consider here. An exotic R4, there exist exotic R4s with the following properties. First of all, they are not smoothly periodic. R4, of course, is topologically periodic, but this kind of exotic R4s have non-periodic ends in the smooth category. Okay, first point. This is for free. It's a property that is known for this class of exotic R4s. Second, cannot be smoothly embedded in S4. These are called a large exotic R4. This is not very important for what we are going to talk now, although it's important for proofs. And exists a rigid block. There exists a rigid block. Again, this comes from the theory of four-dimensional manifolds of a smooth structure in exotic structures in R4s. And moreover, there exists a filtration of rigid blocks such that one is contained in another for a continuous parameter. The interior of these blocks are also exotic R4s. And each one of them are not pairwise, they are pairwise non-diffeomorphic. So it's a continuum of exotic R4. There are a lot of wild properties in these exotic R4s. And moreover, this rigid block cannot be embedded smoothly inside the previous one. So it's not only that they are not diffeomorphic, it's much more strong than that. So in our paper of 2018, Paul and myself show that the previous family of large exotica, a little bit larger than this, but this is important now, are C2 exotic non-leaves. But with the criterion that I talked in the beginning, it's not so surprising now that these are non-leaves. Because you can provide almost rigidity, it's non-periodic, one end, so essentially fits inside that general criterion for C2 non-leaves. What we get in 2021 were exotic non-leaves with infinitely many ends, but here we are able to reach the regularity is 0. Regularity is 0. These examples topologically are the complement of infinite closed subsets of a tame embedding of a Cantor set in a simply connected 4 manifold. Okay, here another question that is not here written, but you have a lot of wild embeddings of Cantor sets in S4, S3. So are the complements of these wild embeddings leaves or foliations? I don't not know, but it's also an interesting question to work with. Okay, this is topological what we were able to do in that paper, and in that paper, it's important that the number of ends is infinite. It's important for the construction. Codimension 1. Okay, we left codimension 1 time ago. RC10 non-leaves for codimension 1 foliations. Okay. Question, and this is also in some problem set, probably 2012 or 2003. If some exotic R4 is a C1 non-leaf or C10, because C2, as we said, is not so surprising. And here we are going to talk about what should be the example. This is work in progress, so probably things should be done, still be done, and still be proved. But here is the main idea.
Sorry, Carlos. So we have a question.
Yeah. A question. Yeah.
Are the results about
About non-leaf for coordination and this results about non-leaf for coordination 1. But this was time ago, no?
No, it's still.
The results of Steve Harder, if there are in that paper of manifolds which are not leaves of manifolds, there are, if I remember, are 2 sections. One is address problems in codimension 1, and there are another part that works in any codimension. That is the part that I talked about that thing, about the entropy of foliation. This results works in any codimension. But except of this part of entropy, all the talk is related to codimension 1 foliation. I don't know if this answers the. The results with Paul. Well, I'm not sure. The results with Paul. I'm not sure what are the results with Paul. Probably Paul knows, but there are several. So on the board now. This 1 minute ago. This one. This is a result of Paul with me. Yeah. These results only are codimension 1. The results are codimension 1.
Okay.
Yeah. Only the part of the entropy is the unique part of the talk that works in higher codimension. This is codimension 1. And even codimension 1 is very hard, the problem. So, what kind of exotic R4 should be a C10 non-leaf? So, set this as the end sum operation. Then sum is the analogous to the connected sum for open manifolds, for non-compact manifolds. Just take 2 semi-infinite proper paths going to infinity in both manifolds. Take a tubular neighborhood, remove this tubular neighborhood, and glue the boundaries. This is what is called an end sum, and it only depends in the isotopy class of the path. But in the case of R4, there are no dependence on the path, because R4 is trivial at infinity. So then sum has no problems to be performed here. Of course, the tubular neighborhood must be small in order to be standard, but this is the unique thing that you have to take into account. And here we set a monotonous decreasing sequence of parameters, decreasing. and of course convergent to some value. And we make then some of the interiors of rigid blocks that we spoke previously. This is called arrow infinity. This should be an example of a C-Win0 non-leaf, and the idea is that this is work in progress, is that this is rigid. This is rigid, not almost rigid, it's rigid. And moreover, it has infinitely many pairwise disjoint rigid blocks, not just one. It's more or less apparent that you have here infinity blocks, but it's not clear that they are rigid. They are rigid in the previous manifold, in the previous exotic, but when you make the end sum, it's not clear at all that they are still rigid. In fact, it is almost false that they are rigid, because for a given Tn, you can repeat it in the previous ones easily, because it's embedded, naturally embedded. But you can only repeat finitely many times. Finitely many times. Yeah? This is the reason to take here a monotony decreasing sequence. So what we are going to show is a very birth property, that any self-diffeomorphism of this guy in any rigid block, you have a compact invariant set inside the rigid block. So you have infinitely many compact invariant sets going to infinity for any diffeomorphism. Okay, this is not simple to show. This is work in progress, but hopefully is true. And this is the K that allows to show this. And the idea is this one. Here is the method of proof of Etienne for a non-leaf. If your manifold is rigid, assuming that is realizable, if realizable, it can be realized in a trivial product. So the union of leaves diffeomorphic to this one forms an open set, saturated open set. So you can consider the union a connected component of this open set. Following the same G's method of proof, and the Hector's lemma is K here, the open set fibers over the circle, and the monodromy of the fibration acts non-trivially in the leaves. And the monodromy is a diffeomorphism of the leaves onto itself. So, if we consider the octopus decomposition of the metric completion of the saturated open set, we have a nucleus and we have an arm. And the monodromy in the arms takes every point to infinity in some sense. Are not the orbit of a point in the arms is not unbounded by bounded by the monodromy map. And moreover, this property is not only true in the arms, it's also true close to the boundary of the omega, because the monodromy close to the boundary goes in a direction. The monodromy is going in the transverse flow. Yeah. The problem is that for some regions escapes from infinity for the monodromy, and in other regions escapes to infinity for the inverse of the monodromy. Okay. So a rigid block can be realized only if meets essentially the nucleus, and if meets the region, the escape region, it must meet the escape region for the inverse of the monodromy and for the monodromy at the same time. Since each rigid block contains a compact invariant set for the monodromy map, and we have infinitely many, some of these compact invariant sets must be out of the nucleus, of the core of the nucleus. And this is impossible because the monodromy does not preserve any compact invariant set. Okay? So this should be the contradiction. So all depends, of course, in this proposition. That this property is true, that this is in progress, since that is true, but there are lots of things to do, still to do. But I think that it's interesting to present here the finish of the work that I begin with Paul. That if an exotic R4 can be a leaf of codimension 1 foliation, and after 10 years, or almost 10 years, be able to produce an example that finishes solves the question. So I think that this is for the talk. Well, this is a representation of a nucleus and the monodromy, but I think that the idea is clear. So thanks for your attention, and parabéns, Paul. Hope to meet you more frequently in the future, if it's possible.
So thank you, Carlos. Don't know if it's working, so
Yeah.
so thank you very much for the talk. So we have some questions, some comments. So we have some questions on YouTube. So I think we already have many questions and comments during the talk here. So we can thank again the speaker. And so we have a break, for a coffee break, like something 15 minutes, before we don't be so late. So, and then we come back for the talk of Professor Duza.